this next type of factoring is a very specialized type of factoring, and it doesn't get much mention in Algebra 2 just because there's other ways to handle it. But it's very important when you start looking at how you would complete the square when you solve quadratic equations. And we do come back to this type of trinomial time and time again. So we're going to treat it as its own special type of factoring. It's worth learning because it's not really all that difficult. All right, when we talk about a perfect square trinomial, we have already checked to see if the greatest common factor is 1 or not. And if you have a greatest common factor, you still have to factor that out. We don't ask, is it the difference of two perfect squares? Because clearly we are dealing with a trinomial now. So we move on to, could this be a perfect square trinomial? That's the question we're asking. And if the answer is yes, it factors very, very easily. So it's just a simple check. That's where all the work is. Check to see if this is a perfect square trinomial. Right? And I call it a threefold check. And there are three very easy things to check. Check number one, the first thing you look for is ask yourself, is that a perfect square? Your first term. Perfect square. And if you say yes, well, okay, it could be a perfect square trinomial. That's the first check. Now, if you say yes, write down what it is, okay? What two things that are exactly the same multiply to be 4x squared? You would say, well, yeah, it's 2x times 2x. Okay, great, but that doesn't mean it's a perfect square trinomial. That just means you go to check 2. Check 2, take the last term. Now, that must be plus. If it's minus, it fails. This is not a perfect square trinomial. So if this is plus, and it is also a perfect square, so is the first term a perfect square? Yeah, 2x times 2x. Is the last term a perfect square? Yeah, it's 5 times 5. And actually write that out. That's 2 checks. Now the third and final check, if it meets those first 2 requirements, then you simply take one factor of each of these. This is why we wrote them down here. We take a 2x, we take a 5, and you actually multiply those together. So a 2x times 5 multiplied gives me a 10x. Multiply that answer by 2 and see if that's your middle term. So multiply one of each, double it, or multiply that by 2. Ask yourself, is that your middle term? Now, we don't care if the middle term is positive or negative. That doesn't matter. That can be fixed when we actually go to factor. So 10x times 2 is 20x. Yeah, clearly that is our middle term. Again, it's minus here, but that doesn't matter. Once you go through that threefold check and all things are true, it factors so easily. So, is the first term a perfect square? Yep, 2x times 2x. Last term a perfect square? Yeah, 5 times 5. If I take one of each and multiply them together, I get 10x. Immediately double that, you get a 20x. Is that my middle term? That is. So once you go through that trouble, it's very easy to factor because it always factors into one binomial to the second power. In other words, it's 2 binomials, but they're exactly identical, so why write them twice? Let's just write it as a quantity squared, and it's very easy. Whatever you circled here goes in there, the 5 goes in there, and here's where we adjust for the middle sign. The middle sign is plus, well then that's a plus. The middle sign's minus, so all we're going to do is steal that middle sign. It's 2x minus 5 quantity squared, or 2x minus 5 times another 2x minus 5. That's what makes for a perfect square trinomial. Pretty easy once you get through the checks. All right, so again, don't forget about greatest common factor. Always be looking for that first. But once you get to a trinomial after the GCF, this should be one of the first questions you ask. Is it a perfect square trinomial? So let's just take another example. Say we had 100x squared. Oh, we got 60x plus 9. All right, well, the first thing we look for, again, is what's the greatest common factor. Now, it's probably easiest to look at the smallest number, in this case 9, and think of the factors of 9 and then test them out against the bigger numbers. Well, I know 3 goes into 9, but 3 doesn't go into 100. 9 goes into 9, but 9 doesn't go into 100, so greatest common factor is 1. I'm not asking, is this the difference of two perfect squares? That's a silly question. I just go right on to, could this be a perfect square trinomial? So, first term, is that a perfect square? Answer is yes. It's 10x times 10x. Last term is positive. That's good. Is that a perfect square? The answer is yes. It's 3 times 3. Now, we have to take one of each. So that's 10x times 3. We multiply them together to get 30x. Don't forget to multiply that answer by 2. Double it. And see if that's your middle term, which it is. 30x times 2 is 60x. And it's even positive, but that's not really our concern. So once we decide it's a perfect square trinomial, we'll just say it's two binomials that are identical, so we'll just write it as quantity squared. 10x goes in the first, 3 goes in the second, just as you see it there. That's plus, so that's plus, and that's completely factored. Right? It's a great time saver because these trinomials traditionally are difficult when there's a number in front of your x squared. That we'll see as we move on here. Okay, speaking of those, let's call this fourth. And this is just trinomials, plain old trinomials. Once you get past, well, it turns out this is not a perfect square trinomial I'm looking at, well, then we're dealing with just your run-of-the-mill trinomials. Now these, we generally, I call it unfoil. You might remember this as using the X method in some of your classes, where you would draw an X and you'd put numbers in all 4 of these spots to figure out how this would factor by grouping. That's actually not how I show it. So if you're comfortable that way, definitely do it that way. I'm just going to do my examples as unfoiling. Right? So as an example of this unfoil process, we might have a trinomial such as x squared minus 3x minus, let's go 28. Okay, first off, the greatest common factor very quickly we can see is 1. Second, is this a perfect square trinomial? Well, x squared is a perfect square, true. X times x, negative 28, is definitely not a perfect square. So forget that idea. Next, we go to, okay, how would this unfoil? Well, when you unfoil, well, let's think when you foil, you do first, outer, inner, last. Now, when you unfoil, what goes in the f of foil, the first slots, has to multiply to be this term. So, since it's x squared, I'm just going to say x and x. That's all I can think of. Right? So, when we do the f of foil, we will get x squared. Likewise, since that's the f of foil, this negative 28, that's going to be the L of foil. In other words, what you put here and here have to absolutely multiply to be negative 28. They have to multiply to be this last term. Now, there's where the problem is. There's plenty of numbers that multiply to be 28, negative 28. We can go through them. It's negative 1 times 28. That does it. Also does 1 times negative 28. Those both multiply to be negative 28. Negative 2 times 14 does. So does 2 times negative 14. Negative 4 times positive 7. 4 times negative 7. As far as integers go, you got 6 options. There's 6 factor pairs that multiply to be negative 28. Well, the whole idea is, what haven't I considered yet? I haven't considered outer and inner. Well, this negative 3x is made up of the outer plus the inner. In other words, since this is just a 1x here, we can just look at these numbers here. These are the numbers that multiply to be negative 28. What we're now looking for in this problem is which of these 6 will add up to be a negative 3. So we listed all 6 that multiply to be negative 28. Now we got to consider outer and inner that have to end up being a negative 3. So if I take negative 1 plus 28, that adds up to be 27. That gives me negative 27. 12, negative 12. 3, negative 3. That's the winner. So all of them multiply to be negative 28, but only one adds up to be a negative 3. Be a positive 4 and a negative 7. Now, we don't necessarily have to list out every possibility. A lot of times we can think about it for a couple seconds and figure out what it would have to be. But in this unfoiling process, it's actually pretty simple when there's a 1 in front of this x squared. So, a quick check. If you do the f of FOIL, you can easily see that you get x squared. And we needed an x squared. When you do the O of FOIL, it's a 1x times a negative 7, which gives you your negative 7x. The inner of FOIL will be 4 times 1x, or 4x. And the L of FOIL, well, that'll be 4 times 7, which is negative 28. So what you're doing when you're factoring these, you're making sure the F of FOIL gives you this. You're making sure the L of FOIL gives you that, but that's where the rub is, because there's usually several things that will give you this negative 28. And then you got to think, okay, look at the possibilities that give you negative 28 that now add up to B. That middle term, that outer and inner, needs to be that negative 3. And the reason we don't care about the x's is because this was always just x and x. There were no other numbers there, so we really could just say, let's ignore the x's and just concentrate on the coefficients. All right, so that's kind of what I'm talking about when we say unfoil. All right, so let's try the second one. Say we had x squared plus, let's say 13x plus 42. Okay, step 1, always look for your GCF, which is 1. Quickly, this is not a perfect square trinomial, but we can do some unfoiling here. X squared is going to be x and x. What multiplies to be 42? Wait. Multiplies to be 42, yet adds to be 13. Well, first numbers that I thought of for 42 are 6 and 7. And 6 times 7 is definitely 42, and 6 plus 7 is also 13. So these really aren't too bad to factor. We'll see some bad ones in the next video.